friends. In this video we are going to get introduced to definition of open sets and then we will be working with few examples. So let's start with it. The prerequisite for this topic is the idea of open balls in various metric spaces. So let us go for the idea of open set. Open set basically the idea is it is like any open ball or the union of open balls. To be very precise, let us get into the definition. So, the definition of open set in a metric space, we will say, so let us take any metric space XD, we will say a set G is said to be open in X if you take any point P in G, then you should be able to find some RP, some positive real number, we denote it by RP, which will work as a radius, such that the open ball BPRP should be a subset of G. So, the idea is this, if you have a set A I mean set G and take any point P, then around that point I should be in a position to find some open ball with some radius RP such that that ball sits inside the set. This I should be able to do for every point of my set. If I can do that, then I can declare that my set is open, otherwise not. So, to note few points, let me mention the points again, that is if G is open, then what must happen is around every point, note the point every, we are saying around every point we should be in a position to get some radius such that with that radius the open ball should be sitting inside G. Another point to be noted is this radius certainly may depend upon point P that we are dealing with. So, as we change the point, we may have to change our radius such that the ball sits inside the set G. Then by definition it can be treated that empty set and X are always open sets. Now, with this idea let us get into several examples. So, naturally to start with, let us take a set of real numbers with usual metric, and let me take any two real numbers A and B with A less than B and look at the interval, open interval A to B. We want to say that this is a open set. Now, to say this, what am I supposed to do? So, let us look at the geometry again. So, I have open interval A to B like this, and what is the requirement for this to become open? There should be take any point P, I should be in a position to find out some open ball around this which will sit inside the interval A to B. Now, we can actually see that how much distance I have in my hand to travel so that I will sit inside. So, I have to see the distance of P from A and the distance of P from B, because A and B are the boundaries. So, I do not want to cross them. So, look at both the distances and then naturally I would like to choose the minimum. So, I will be choosing the minimum and going to draw the neighborhood around P, and that will certainly sit inside the interval AB. So, this is the idea, and hence that open interval is going to become an open set with respect to usual metric in R. Now, let me change the set to 1, 2, 3. So, I am now having a set which has only discrete points, point 1, 2 and 3. Now, what do you think, is it going to be an open set? It will not be, because any neighborhood if you look at, if I for example take a point 1 and take any neighborhood of it, it will have certainly many points which are not going to be from set A, because when I take an open interval it has infinitely many points, whereas my set A is finite, and hence with that logic we expect A not to be open in R with usual metric. Now, going ahead, let me take the same space, same metric, but changing the set to set of natural numbers, and I am sure it is quite easy to guess that it again will not be open with the similar idea that one can use to justify. Going ahead, let us take set of real numbers again, usual metric, and now I am changing the set to an interval where it is closed 0 to open 1. Now, again the situation is almost similar, because if I take close 0 to 1, interestingly for every point between 0 and 1 you will be able to find out some radius around that point to sit inside the set, but at 0, because 0 is also a member, I should be in a position to find some radius around 0 which will sit inside the set, but that will not happen because the left side of that particular interval is not going to be a part of my set A, and hence this again will not be a open set in R with usual metric. Now, let us deal with something different. So, let me ask you a question. Consider R with discrete metric. Now, which of the following statements is or are true? So, statement 1 is saying A equal to 1 to 3, 1 comma 2 comma 3 is an open set. Another statement is open interval 4 to 5 is an open set. Closed interval 0 to closed 0 to open 1 interval is an open set. So, interestingly, the answer is 4, that is all the above statements are correct. That means what we are trying to say is all the sets A, B and C are open. So, let us justify the statement in general in fact. So, let us go for a discrete metric space. So, let XD be a discrete metric space and let me take a singleton set to begin with. I want to say that this singleton set is open. Now, what do? I just need to find one open ball around that particular point which will sit inside, and you can see it is, if I take B p comma 0.5, we already have seen the structure of open ball in a discrete space, hence we can see that it is singleton P which is inside G. Hence, I get every singleton set to be open in a discrete metric space. Now, look at, take any set which is non-empty and which is subset of X, then can I write it like this? Yes, I can write it as union of all singletons where each X is taken from my set A. Now, we know already singleton is open, and although we have not proved, but intuitively we may feel that union of open sets should be open, and hence I am going to have my set A to be an open set. By the way, let me mention here that we are going to prove the statement union of open sets is open in our next video. Now, this means that every subset of a discrete metric space is going to be open. So, for a discrete metric space, the structure of open sets is very much clear. In fact, every subset of a discrete metric space is open. Now, I want to move to an important result, that is, if you take open ball in any metric space, then it is going to be an open set. Now, if I want to prove this, let us begin with the proof. So, let me pick up some metric space XD and let us take some BPR open ball in XD. Now, I want to show that it is open. I am just taking some set A, let me declare A is equal to BPR, and we want to prove that A is open. Now, to prove A is open, what is our duty? Our duty is to take a point, any point from set A, and try to find out some open ball around that point which is going to sit inside set A. So, situation is this, you already have one open ball which is actually BPR, P and R, and what I have done is I have started with some X, and now I want to select the radius which will solve my purpose. Now, you can see that I do not want to cross this boundary. So, if I do not want to cross this boundary, obviously this is what the radius that I would like to take. And what is this? This is, you look at the total radius R and then remove this much distance, that is precisely the distance between X and P, and hence the suggested radius could be R minus the distance between X and P. And this guess is perfectly alright because this is a positive value and one can prove that with this radius the open ball will sit inside A. Let us see quickly how to deal with it. So, we have dxp less than R, as suggested S is R minus dxp, and hence you can observe that if I start with any y in Bxs, then dyx is less than S, which is equal to R minus dxp. So, simply I get dyx plus dxp less than R, but then apply triangle inequality. So, dyp becomes less than R and hence y becomes a member of set A. So, in this sense what I get is every open ball in a metric space is an open set. Now, quickly let me get into the open sets in R2. So, let us deal with a few examples. The first example is in R2 with Euclidean metric to begin with. Let us deal with open 0 1 cross open 0 1. Now, how does the set looks like? So, let me draw it over here. If I am taking open 0 1 cross open 0 1, that means x coordinate as well as y coordinate lies between 0 and 1. So, this it cannot take values 0 and 1, and hence it is this portion interior of the rectangle of the square excluding the boundaries. Okay. So, now if somebody gives me any point, if I start with any point P in this particular set, then what I would do is I would like to, I do not want to cross these 4 boundaries. That means, I want to find out the distance of this point from each of these boundaries. So, I can get all 4 distances simply, and then I want to choose the minimum between those. So, that will be the radius for which will work to show A is open. Secondly, you look at set B. Now, what is set B? It is x1 into x2 equal to 0. That means, it is simply going to consist of x axis union y axis, that is those 2 axes only are there in my set. And now, if I take any point, say maybe for that matter 0 0, then what do you think? If you take any open ball around that, then it will certainly have lot of other points, namely over here, which are certainly not there in my set, and hence this set B is not going to be open. Whereas, if you look at set C, then it is, so it is all those points which are lying for which the addition of the coordinates lies between 1 and 2. So, I would like to plot the lines x1 plus x2 equal to 1, it is this line, and x1 plus x2 equal to 2, it is this line. And so, this is the portion that we want to talk about, excluding the lines. So, the region between these 2 lines is what the region that is there in my set. Now, if I take any point P, then what I have to do is, again I do not want to cross these 2 lines, that means I have to get the distance of this point from this line and the other line, and then select the minimum. If I take that as my radius, then it can be proved that the corresponding open ball is going to lie inside the given set. So, this is the idea of open sets along with few examples. In the next video, we are going to work out some interesting properties of open sets.